Okay, what did you come up with? What is this, the hydrogen sulfate ion? Is it an acid or a base in this chemistry? It's an acid. And what is its conjugate base? HPO4 negative 2 has one proton different than the hydrogen sulfate? Sulfate ion is its conjugate base. Acid-base pairs differ by one proton. Okay? Oh, yeah, that was real different. What is this? A base. And where is its conjugate? This is its conjugate acid. Okay? And how about down here? What is this? It's a base. And what is this? H2PO4 minus. It's an acid. What is the conjugate acid of the hydrogen carbonate ion? Carbonic acid, H2CO3. And what is the conjugate base of the dihydrogen phosphate ion? So, wait a minute. Up here, you told me that was an acid, and down here you're telling me the hydrogen phosphate ion's a base? Is that right? Yeah, it's right, because it's in relationship to something else. So this is our first example of something that can behave as an acid or a base. It likes to swing both ways, and we call that amphoteric or amphiprotic. It's things that can have either acid or basic behavior. When you look at this, if you have things like the hydrogen sulfate ion, where this started out from the acid H2SO4, this has only one proton left. It's still an acid. It can be an acid or it can be a base. Sometimes because one proton is gone, it's called a hemiacid. Sometimes it's called a half acid. I like that. I think it's funny, okay? It's a half acid because half its protons are gone. So if we look at hydrogen carbonate, when it's reacting with the hydroxide ion, this is the acid and this is the base. And it makes a new base, the conjugate base of carbonic acid, and it makes a new acid, water, which is the conjugate acid of the hydroxide ion. Now, the hydrogen carbonate ion can also react with a different acid. So in this case, when it reacts with hydronium, it's the base and hydronium's the acid, and the carbonic acid is the acid, and water is the conjugate base of the hydronium ion. So things can go both ways. Water is amphiprotic, the hydrogen carbonate ion is amphiprotic. Okay, look at water here. When it reacts with HCl, it's a base, and this is an acid. Hydronium is the conjugate acid, and chloride is the conjugate base of HCl. Water can also react with ammonia. In this case, water's being the acid and ammonia's being the base, to make ammonium the conjugate acid and hydroxide the conjugate base of water. So there are a lot of different species that have this two-way behavior in solution. Now, when we start to think about acids, it's going to become important that you recognize things by their formula at a glance and that you know what kind of acid they are, or if they're an acid or if they're a base, and what they're going to do in water. So, there are 7 strong acids. You were introduced to these in Chem 111 and told, learn these because you'll need them later. Do you all remember these 7 strong acids? Or do you all at least remember being exposed to this before? Okay. So now, if you don't remember them at a glance, I don't know, do what you do. Make flashcards, whatever, to try and memorize these so that you will recognize them. Presley? Ho. Nobody can punch Santa. What's ho? Oh, that's ho, ho, ho. Nobody can. Where's the P? It wasn't clock Santa, was it? Nobody can clock Santa? There is a phosphoric acid. It is not a strong acid. Nobody can clock Santa. Yeah, I'm curious about that. I don't know what the P is for. What do you think it was phosphoric? Phosphoric acid is not a strong acid. I don't know. All right, I'm going to chase that guy down and ask him. Sure, go ahead and take a peek at it. And then you can go in e-learning and email the whole class and tell us. Okay, you know how to do that from the class list drop-down menu? Log into this in e-learning, and at the top menu bar it says class list. If you click on that, there's a thing to click email, and you can email everybody with one click. Yeah, I'm curious. It's kind of cute, and if it's something that can help us, that'll be good. But I'm thinking punching Santa was cute. Oh, come on. Don't you ever get tired of Santa? Ho, ho, ho. Yeah, right. Merry Christmas. No, it's not one time a year. It starts before Halloween. It makes me crazy. Yeah, well, that makes me crazy too. Especially if they're turning them on. But they look so pretty. When I'm walking the dog, I like that. All right. Sulfuric acid is different. Santa acid. And it's different because it has 2 protons and only the first ionization is strong. So for sulfuric acid, you have H2SO4, and it's a one-way street ionizing completely to the hydrogen ion plus the hydrogen sulfate ion. Now the hydrogen sulfate ion loses the second proton, but this one is in equilibrium. So we're not going to use sulfuric acid in our examples as much because it's different. And because the conjugate base of sulfuric acid is actually an acid in its own right. It's one of those hemiacids. Well, it is balanced. This is one balanced equation, and this is a balanced equation. They're just overlapping. Oh, that's it. Okay. Thanks. Yeah, chloric, perchloric. But still, I don't get ho, ho, ho. How do you get a ho out of chlorine, bromine, and iodine? I don't know. An oxygen. The ho is missing oxygen. That makes me think of something else, but we won't go there. All right. Okay. Weak acids. Now there was no joke. Weak acids. We're going to